In this lesson, we're going to look at the composition of different transformations. So we're going to put together a couple of the different transformations we've looked at. These are called glide reflections, which is when we first make a translation, then we follow it by a reflection. In this first example, we're first asked to translate our coordinates x, y, so the three vertices of the triangle, to x, y minus 3. Then we're asked to reflect this across the y-axis. So step 1, let's translate all of the coordinates using this first translation. There's no movement in the x direction, so everything is just going to move down by 3 units. A moves down 3 units. We are A prime right here. C moves down 1, 2, 3 units, and we have C prime. And then B moves down 3 units, and we label it B prime. Connect them up. Now, to the right, I do ask for the coordinates. So the coordinates of A prime are easy enough to follow just by reading them off. So again, you start at the origin, shift over, looks like 5 units, so that'd be -5, and down 1. -5, -1. The others are found just the same. Now, the second step is to take the reflection across the y-axis. So we're going to reflect across this vertical line here. So that's our mirror in this case, and each point needs to be reflected at a right angle. So C prime is 4 units away from the line of reflection, so we're going to go 4 units in the opposite direction. Notice when we're reflecting across the y-axis, what happens to the coordinates is the x value swaps signs. So now this is +4 and -3. So again, the sign has just switched in the x component. And that's going to be the same for all of them, which leaves us with +5, -1, and +7, -2. To plot those points, we've got +5, -1 showing up here. And then for B double prime, +7 minus 2 here. And we can connect all of those points. Make sure you're labeling them as well. So we have A double prime, the image of A prime, C double prime, and B double prime. So this triangle ABC double prime, all of them, that represents our glide reflection. A second example of the composition of transformations is a translation, which we're then going to follow with a rotation. So we'll start with the translation. And the translation is defined by changing the x value by adding 4 to it, and the y value moving it down by 2. So each of these values, we're going to move over 4, 1, 2, 3, 4, to the right and down 2. And I'm going to do that for all of them. So here's C prime. A is going to move over 4 and down, so this is going to be A prime. And then lastly, B, moving to B prime, would be right here. And I can connect that figure. So now this is the image of my original triangle. But now I have to rotate this 90 degrees about the origin. Remember that for a rotation of 90 degrees, what we do is we take A and B, and the translation is reversing A and B, but making B now negative. So it's the negative y value, comma, the previous x value. I think this is a bit easier if we first list the coordinates of A prime, B prime, and C prime, which gives us -1, 0 for A prime, -3, -1, which is B prime, and C prime is 0, -2. So now to find A double prime, the rotation of my prime image, I have to switch the x and y values and change the sign of the new x. So I'm going to first switch them. -1 and 0 swap around, and I make the 0 negative, but 0, -0, they're the same thing. So my new coordinate is A double prime is 0, -1. B prime, first start by swapping the two, -1, -3, and then changing the sign of my new x value. So it's going to become +1. And then C double prime, swap the two, -2 and 0. but the x value now becomes positive. Last step, I have to graph all of these. 0, negative 1 will be my a double prime. Positive 1, negative 3, b double prime. And c double prime at 2, 0. And now I've shown the composition of the transformation, coming up with my image being the final prime image in the red. You may have stood in front of a few mirrors before and been wearing a shirt that had letters on it and realized that in one of the mirrors your shirt read all of the letters in reverse or flipped upside down, and then the other one the words were able to be read again. And this is a property that we can study. So what we need to have happen is we have two mirrors, for example, or in this case two lines of reflection, K and M, that are both parallel to one another. And what happens is you start with the original image, so the pre-image, and that pre-image is reflected across the first line, giving you Q prime and P prime, which is then reflected again. And this brings you back to the original image. It's the same orientation, however now it's been shifted over, so it's been translated. So if K and M are parallel, then the reflection in line K followed by a reflection in line M is the same as a translation. This brings up two important points. So we're going to look at P prime, and this is the image of P. And what happens is the line segment formed between P and P prime has to be perpendicular to both lines K and lines M. And we've looked at that before in terms of reflections and how they land at a perpendicular angle to each of the mirrors. Second, P prime, which is the segment formed from P to the image P double prime, has to be 2 times or twice the distance between these two parallel lines. Why this makes sense is the distance from P to K should be the same as the distance from P prime to K by the properties of reflection. And similarly, the distance from P prime to M should be the same as P double prime to M based on the properties of reflections. So what we can do is add them together. We have the distance here is represented by the blue segment and the red segment, and the distance on the outside is also a blue segment and a red segment, so that's twice the distance. Using these properties, we have, again, two parallel lines given here, and we have line segment CD is reflected about the line R, giving us C prime D prime, which is then reflected about the line S. First question is, translation maps segment CD onto which segment? Well, this translation is going to move C over to C prime and D over to D prime. So this is going to be segment C double prime, D double prime. Perpendicular to line D, D prime. Well, let's form that line first. So we have this line here, what should be perpendicular to each of the lines by the properties of reflection. So which lines are perpendicular? Both lines are perpendicular, line R and line S. Looking at segment C, C prime, we're asked to name two segments that are parallel to C, C prime. So clearly one of the segments could be D, D prime, and then a second one could be D prime, D double prime. So we'll write D, D prime, which is parallel, and D prime, D double prime. Now, we know that these are parallel because we have that this segment is perpendicular to both of the lines. So we have two lines that are both perpendicular to the same lines, making them parallel. Given that the distance between R and S is 2 inches, meaning the distance between these two lines is 2 inches, when asked what the length from C to C double prime is, all we have to do is take and double that, because this total length is going to be twice the distance between the two lines. So 2 times 2, which is 4 inches. Lastly, we want to know, is the distance from C prime to C double prime equal? Are those congruent? And as you've already studied, by properties of reflection, these must be congruent. The reflection from C prime to the line and the line to C double prime are the same exact lengths, So yes, they are the same distance. Don't pay too much attention to the name of this theorem, but rather how to use it. This picture is a pretty good representation of the theorem, but I'm going to draw it out as we construct it. So what we're going to do is we're going to take two lines. We're going to take the line K and the line M. And these two lines are going to intersect at one point. This point I'm going to label as P. A reflection in K. So if we start with some point, let's just put it right here, and we reflect it about the line K. So what we're going to do is take this point and drop it perpendicular and then put the same distance over here. The reflection about the line K. So it would end up somewhere about there. And let me label this point. I'll label it A, so its reflection is A prime, the image of A. And then I'm going to reflect that one more time about the line M, so right across here. And I'm going to label that A double prime. And what this theorem says is, if you reflect across two intersecting lines, it's the same thing as a rotation about the point P. So where P is the center of rotation, point A is now being rotated about some degree measure around to A double prime. And we can actually figure out what the rotation is. What we can do is we take the angle between the two intersecting lines. And what we want to do is take this angle. We'll call it x degrees. We do not want to look at the larger angle. We want to look at the acute or 90-degree angle. So do not look at this larger angle, but rather the angle in between like this. And the rotation is actually twice this value. So 2 times x degrees is going to be the angle of rotation. Putting the last theorem to work, we've got t, which is then reflected across the line K and then reflected across the line M. So this is going to represent a rotation since it's reflected about two lines that are intersecting at point P. So now point P becomes the center of rotation. And what we have is, we're going to focus on the point here, this point T rotating all the way around to T double prime. So it does one of these. And to find the angle of rotation, what we have to do is look at the acute angle between, which is 75 degrees, and multiply it by 2. So here we just take 75 degrees times that by 2, which equals 150 degrees. So this is a rotation of 150 degrees. One last example that we'll walk through is a glide reflection. So we're first going to translate this triangle and then reflect it about the line y equals x. Step 1, the translation. Here we're giving a vector that represents the translation. So we have to take each point and move it to the left 4, since it's negative 4 in the x direction, and down 3 by negative 3. So we'll take C over to the left 4, down 3, gives us C prime right here. A prime is going to be same thing, over 4, down 3. A prime. And then B prime right here. Connect up those points for my image of the original triangle. Digging up our formulas that we used earlier, to reflect about the line y equals x, we can take the point AB and swap its components. So this becomes B comma A. So each of these points, we can find the coordinate point and just swap them around and then plot it. And keep in mind graphically what it means to reflect across y equals x. That's this line here. It's the line of slope positive 1 that goes straight through the origin. I find it helpful to first find our A prime, B prime, and C prime coordinates. A prime being negative 6, 0. B prime negative 5, negative 4, and C prime negative 8, negative 3. By listing it that way, now it's a lot easier to actually plot the others because I'm just reversing the points. A double prime, swap the 2, 0, negative 6. B double prime, swap the 2, negative 4, negative 5. And finally, C double prime, again swapping negative 3, negative 8. Last up, I have to plot these points. I've got 0, minus 6, and I'm going to label that as A double prime. Negative 4, negative 5, B double prime. And C double prime at negative 3, negative 8. So it goes off the coordinate plane a little bit, but that's alright. I can estimate best possible, and then connect the points to form your triangle. And we're done. I want to warn you that when you are doing these, couple things to point out. Just make sure you're labeling everything each and every time. Notice I labeled A prime, B prime, C prime, A double prime, B. Keep that going, because if you don't do that, you're going to get confused, and I'm going to get confused as to what your intentions were when I'm assessing you and evaluating whether or not you understand the material. So just be consistent and accurate as possible.